Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, number of ways to stay in the same place after some steps. This is an interesting problem. We're given a pointer which starts at index 0, and we're also given an array of this length, but we're not actually given an array. The problem is actually more simple than that. We're basically just told like how long the array is. We start at index 0 and we're going to be taking 3 steps. So assume that this is an array. It's just of size 2, I guess, and we're starting here at index 0, and there's also index 1. The array doesn't really have any values. Even if it did, we don't really care about what the values are. But assuming that we start here at index 0, for every single step, and in this case, we have to take exactly 3 steps, for each step, we have 3 choices. We can either move to the left, or we can move to the right, or we can just stay in the same position. Now, of course, in the beginning position, we can't really move to the left. So in this case, we actually have 2 choices: stay in this spot or move to the right. What we're trying to do here in this problem is count the number of ways that we could take exactly 3 steps starting at index 0 and also end up back at index 0. How many different ways is that possible? Well, to count it with like the brute force, we would start at index 0 and basically make up to 3 decisions each time. Basically backtracking, we know for the first step, we can only make 2 decisions. We can either stay at index 0 or move to the right to index 1. And then for this spot, we have 2 more choices. We can either stay here or move to the right by 1. And here again, 2 choices: stay here or move to the right. Now, what about here? What are the decisions? Well, there's actually, again, 2 decisions. We can either stay here, stay at index 1, or move to the left. And I guess I'll write it the other way: move to the left, which would land us back at index 0, or stay put. Now, of course, if the array was longer, for some of these branches, we would have 3 decisions. Like we could go to 0 or 1 or 2, but it's not longer. So this is actually a bit more simplified, but the concept is the same. We will enumerate all of these paths, and I'll kind of finish it up. Here we can stay at index 0 or go to index 1. Here, same thing, 0 or 1. Here, same thing, 0 or 1. And you can count the number of different paths that we had. In this case is 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, among all of these, which ones landed us back at index 0 by the end? I count 1, 2, 3, 4. So in this case, the result is going to be 4. And that's pretty much the whole problem. If you know what dynamic programming is, aka, well, in this case, if you know what memoization is, you can take this brute force solution and optimize it. What are the parameters that we're keeping track of as we are going through this decision tree? Well, the first one is the index that we're at, index I. That's what this value like represents as we're going down this decision tree. But also, if you notice, we stopped at this level in the tree. Why did we stop there? Because in this problem, we're only allowed to take 3 steps. We have to take exactly 3 steps. So here I counted 1 step, 2 steps, and then 3 steps. So another parameter that we're keeping track of is the number of steps that we've taken so far. And once that reaches 3 in this case, or whatever the parameter is, then we have reached the base case. And then we will return 1 if we were at the index 0. And if we were not at index 0, we don't return anything. We return 0 to indicate that this path is not valid, but this path was valid. So when you have these 2 parameters, we can apply caching to this, aka memoization, and then solve this problem a bit more efficiently. Now, what is the time complexity of this approach? Normally, we just take the input parameters, in this case, I and the number of steps. What is the range of possible values that I could be? Well, up to the length of the array, of course. So the overall time complexity, let's say n is the number of steps and m is the length of the array. The overall time complexity is going to be this. This is the solution space. And the memory complexity is also going to be that. But there's actually a catch here. The time in memory is actually even more efficient than this, and it's not super obvious why, but once you know it, it's pretty simple. Take this array. Let me actually redraw it. In this case, our array length is 5. We have 5 spots in the array. But what if the parameter for steps was only equal to 2? Well, we know we start at index 0. And if we can only take 2 steps, the furthest we could possibly reach is index 2. So for us to say that the overall time in memory is n times m is a bit misleading, because if the number of steps is less than the length of the array, then we can actually take this m term and actually make it an n term, where n is, remember, the number of steps, m is the length of the array. So in other words, the time complexity is not n times m. It's actually the minimum of n and m multiplied by n here, because first of all, this is the number of steps. We have to take that many steps. Like, our recursive tree has to be that height as we build it. The height has to be the number of steps. But the range that our index I could be in does not have to necessarily be the entire length of the array. Now, if the length of the array is smaller than the number of steps, like maybe we're taking 200 steps, well, in that case, again, we're going to take the minimum of that. Like, our I value is never going to be 200. It's going to be within the range of the array. That's why we're taking the minimum of those two parameters. So that's going to be the time complexity and the memory complexity. Now let's code it up. So one thing I didn't mention is that the solution to this problem could be very, very big. So they basically tell us in the problem statement to take the result and actually mod it by this large prime number. So now I'm going to start the recursive solution. I always call it DFS. You can call it whatever you want, but I like to define it in here so we have access to the other parameters. And we know that we just need 2 parameters, one to keep track of what index we're currently at, and to keep track of the number of steps that we have left. I guess that's how I'll do it. You could do it either way. Like, I'll show you how I'm going to call this DFS. We're going to start, of course, at index 0. We could keep track of the number of steps we've taken, in which case I would set this to 0 to start out with, or we could just keep track of how many steps we're allowed to take and then decrement this on each iteration. And like I mentioned, the main base case here is going to be when we have finished the steps that we're trying to take. We have reached exactly 0 steps. And in that case, we are going to return 1 if I is equal to 0, meaning we ended at the beginning of the array. In that case, we return 1. Else, we return 0. Now, the easier way to write this out is return I is just equal to 0, and that will pretty much evaluate to 1 as we add it to the result when we actually make the recursive call. Now, here we know that there are 3 cases, 3 potential decisions to make. The obvious one is just stay in the current position. So we call DFS, we leave I the same, but we still can decrement the number of steps, because technically staying in the same spot does count as a step. So this is what we're initially going to set our result to. But for the other 2, we don't necessarily know that we can make those decisions. For example, if we want to move to the left, we have to make sure that we're not at index 0. We're greater than index 0. So in this case, we're allowed to move to the left, meaning we take I and decrement it by 1. And as usual, we're going to take the number of steps and decrement it by 1 because we're taking a step now. And we're going to take this and add it to the result. We're ultimately trying to count the number of ways. So we're going to aggregate all of these. Now, the other one is if we are moving to the right, and we can only move to the right if we're not at the last position in the array. And we can know that if we take array length and -1 and I is less than that, then we know we can move to the right. So we can call DFS I plus 1 and decrement the number of steps as usual. And we'll take this and add the result to our ultimate result. And then we would just take the result and return it like this. Now there's a couple things that we are going to do to improve this. One, we have to actually use our mod, so I'm going to start with that. I'm going to rewrite these 2 lines as, instead of adding to that, I'm going to take result and add it with this, and then I'm going to mod this by the mod value that we declared out there, so we can ensure that this never overflows. In Python, though, these integers will never overflow, so we can kind of get away with just having this mod at the end, but this is probably the better way to do it. So I'll do the same thing down here, add this, and then mod it. And up here as well, before we set that to the result, let's mod that as well. Now we have the mods out of the way. The only thing left for us to do now is add caching. So let me do that here. I usually use a hash map, and we will check here if we've already computed this subproblem before. If this is in DP, let's return the result that we have already stored here. So I will use that as the key and then just return it. Now, if we haven't already computed it, let's compute it here, which we've already done. And before we return, let's go ahead and add it to the cache just like this. So for this key, let's store the result before we return it. So that's the whole code. Now let's run it to make sure that it works. And as you can see on the left, yes, it does, but there actually is some improvement that we can make to this. We can't really improve the overall time complexity. That is going to stay big O of n times minimum of nm, but we can improve the memory complexity. Currently, the memory complexity is the same. It's this, but we can improve the memory complexity to the minimum of n and m. And for that, we're going to use the tabulation, aka the bottom-up dynamic programming solution. Let me quickly explain that first. So if you notice, when we do the recursive solution, we are computing this sort of solution space, meaning this is like the array. So this is like index 0, this is index 1, and this is the number of steps that we can take or have taken, let's say. Actually, I'll stick with can take. So if we can take 0 steps, how many ways starting from here can we land back at index 0? Probably 1, right? Just by staying here. And if we start here and we're allowed to take 0 steps, then there's 0 ways for us to end up at index 0. So this is kind of the base case because we know we're always going to be allowed to take more than 0 steps in this problem. But this will still help us because now when we want to compute the new subproblem where we're allowed to take 1 step, how do we do it? Well, we know we're starting here, and for us to compute the solution at this spot, we are going to want to make our 3 decisions. And these decisions are going to be the same as when we were doing the recursive solution. This is called the bottom-up solution because we're computing from the bottom. Well, the way I've arranged this, we're kind of going top down, but basically we're starting at step 0, like that's the bottom, and then we're going to step 1, step 2, step 3, which is ultimately our goal. But when we were doing the recursive solution, we kind of compute it in the opposite direction. But now, like I said, we have our decisions. We can either stay at index 0, or we can move to the right to index 1, or we can move to the left, but in this case, we technically can't. But this is the idea, right? This is our decisions. And we're allowed to take 1 step. After we take 1 step, now we have 0 steps to take. So what we're going to do is take the value from here and add it to this position. We're going to take the value from here and also add it to this position. There's no need for us to repeat the work here. So we take those, add them, and then we get 1 here. We're going to do the same thing on this side. We're starting at index 1, but this time we're allowed to take 1 step. So I'm either going to go to the left, I'm either going to stay here, or I'm going to go to the right. We can't really go to the right though. So we take these 2 values, add them together, and we put a 1 here. That makes sense, doesn't it? Because if we're starting at index 1 and we're allowed to take 1 step, then of course we would be able to reach index 0. And this is pretty much what we're going to do for the rest of these as well. So from here, we would take this and this, add them together, we get 2 here. Same thing here, we're going to get a 2. And when we have 3 steps to take, we do the exact same thing. Take these, add them together, we get 4. Same thing here, add these, and we get 4. What value do you think we're going to return? Well, of course, from this row, because we're ultimately looking to take 3 steps, we're going to return a value from this row and probably return the one at index 0 because that's where we are starting at, of course. So in this case, we once again will return 4. Now, this is the tabulation solution, but how does it improve the memory complexity? It looks to me like we still have the number of steps and the length of the array multiplied together in memory. Well, the first thing is notice how every time we compute a row, we only need the previous row in memory. Like we never need to look 2 rows up above or 3 rows or anything like that. So we only need 2 of these in memory at any given point. So that's the optimization. We're only going to keep 1 previous row in memory at a time as we compute the next one. And then we'll kind of get rid of that as we compute the next one here. And then we'll get rid of that as we compute the next one here. So that's 1. That will allow us to only keep a row in memory at a time. So then you might think, okay, well, let's say M is the length of a row. Then we need O of M in memory. But actually, we can do even better because notice how by taking this entire grid and computing it, we have actually lowered the time complexity of our solution. Now the time complexity is definitely going to be n times m, whereas before it was n times the minimum of n and m. So how did it get worse? How can we fix it? Mainly because what if the number of steps is actually less than the length of the array? So let me actually redraw this. So let's say the number of steps was just 1. And let's say the length of the array was actually 4. I kind of inverted it. Well, we know that if we can only take 2 steps, why have the rest of this array in memory? Like we will never reach this part or this part. So we're ending up computing it, but there's no reason for us to do so. We end up having extra memory as well as wasting a bunch of time. So what we should actually do is not compute the length of the array necessarily. We should compute only up until the minimum of the length of the array or the minimum of whatever steps we are taking. So knowing all of these things, now let's code up the most optimized solution. So the first thing I'm going to do is take the minimum of the steps as well as the array length, and I'm going to assign it just to array length. We could use a new variable if we wanted to, but it doesn't really matter because at this point, we're never going to need the original array length again. And we can take a row, I'm going to call it DP. So this is just going to be the row that we were talking about earlier. We only need 1 row in memory at a time, and this is going to be multiplied by the array length. And kind of like I talked about with the base case, we're going to initialize index 0 to be 1, because if we take 0 steps and we start at index 0, well, we end at index 0 as well. So there's one way for us to do that. And now we're going to be computing the solution set for steps where we take more than 0 steps. So from 1 step all the way up until the number of required steps that were needed to take. And steps plus 1 is non-inclusive, so this will end when we are at the number of steps. And now we're trying to compute the next row. I'm going to call that next DP. And so this is going to be an array initially of all zeros of the same length. So array length, and we're going to fill in every value. So I'm going to say for I in range, array length. And now is the part where we have 3 choices. Remember, the first one is really, really simple, where we're going to set next DP equal to the previous DP. That's where we just stay in the same index. We don't move to the left or the right. But the other case is where we move to the left. And we can only do that if I is greater than 0. And if it is, then we will set next DP equal to next DP plus the value at previous DP minus 1, or the index minus 1. That's to the left. And we know that we need to eventually mod this, so we're going to go ahead and do that here. taking this and then modding it by that big prime number up above. And the third choice really is where we move to the right. And we can only do that if I is less than array length minus 1. And in that case, we're going to do pretty much the same thing up above, except now we're going to get the previous DP value at DP of I plus 1, and then mod that by the large prime number up above. And that's pretty much it. Those are the choices that we're trying to make. Before we, though, go to the next iteration of the outer loop, let's make sure to set DP equal to next DP. And then after that, all we have to do is return DP at index 0, because that's where the result is going to be stored. Now let's run this to make sure that it works. Okay, I had a very, very dumb typo here. I had a plus sign when this should be an equal. Sorry about that. Now let's rerun this. And as you can see on the left, yes, it works and it's pretty efficient. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.